This video is going to look at some problems that involve work and how work changes kinetic energy, specifically the work-energy theorem or the work-energy principle. So just a quick reminder on some things. Kinetic energy is defined as energy due to the motion of an object, and the way that we calculate the kinetic energy of an object is 1/2 times the mass times the speed of the object squared. Work for a constant force we're going to be looking at constant forces in these problems. We'll generalize it to non-constant forces later, but for a constant force, work is defined as, you'll often see it written as FD cosine theta, which is the magnitude of the force times the magnitude of the displacement, and the theta in there is the angle between the force vector and the displacement vector. This is often a little bit clumsy to use, and so there are a couple of ways of writing it that are a little bit better as we're trying to use this. So one of the ways is you can take the force and break the force into components. And one of the components can be parallel to the displacement. And so you use that component of the force that's parallel to the displacement, and you multiply by the displacement. That will give you the work done by that force. Another way of looking at it is taking the displacement vector and breaking it into components. And you take the full force and you multiply by the component of the displacement that's parallel to that force. The biggest example of a place that we use this is often when we look at the work done by gravity. We often know the vertical distance that it travels. The force of gravity is in the vertical direction, and so we can use that vertical distance times the force of gravity to get the work done by gravity. Again, the final thing, the work-energy theorem. You'll also sometimes see this called the work-kinetic energy theorem, or sometimes the work-energy principle. And this says that the net work done on an object equals the change in kinetic energy of an object. The change is the final minus the initial. So the net work means if you find the work done by each force individually and you add all of those works together, work is a scalar, you add all of those positive and negative numbers together to get the total work done, or the net work done, that gives you the change in kinetic energy. Because that's what work is. It's the way that we transfer energy to or from an object. So we're going to look at that in some examples. In this first example, we have a book that's sliding along a rough horizontal surface. At point A, it's moving at 3.21 meters per second. At point B, it is slowed to 1.25 meters per second. And part A says how much work was done on the book between A and B. Now, often when people first see this question, they say, okay, well, work is a force times a distance. And so they start reading the question and they say, well, I don't know the force. Oh, well, but it's a rough surface, so it should be friction. But they don't give you the coefficient of friction. So you don't know how big that force of friction is. Also, you need to know a distance, and they don't tell you the distance. But with this, they do tell you the initial speed and the final speed. And so this is where you have to realize that if you know the initial speed and the final speed, and you know the mass of the object, you know the initial and final kinetic energies, which that change in kinetic energy is the work done. So we're going to use the work-energy theorem. We have that the net work done, and that's what it's looking for, how much work was done on the book. So it's asking for the total work done. This is the change in kinetic energy of the book, which is the final kinetic energy, the kinetic energy at point B, minus the initial kinetic energy at point A. The kinetic energy at point B is 1/2 times the mass of 1.5 kilograms times 1.25 meters per second, that quantity squared, which is 1.1719 joules. the kinetic energy at point A is 1/2 times the mass times the speed at A, 3.21 squared. And that gives us 7.7281 joules. And so this net work is the kinetic energy at B, 1.1719 joules, minus the kinetic energy at A, 7.7281 joules. And so we get that this net work done is negative 6.5562 joules. The fact that the net work is negative means that kinetic energy was removed from the object. These forces took energy away from the object. So positive work means that you're adding energy to the object. Negative work means that you're taking kinetic energy away from the object. Okay. Now this book continues on from point B, and now it's moving to point C. And they tell us if negative 0.75 joules of work is done going from B to C, they want us to find the speed at C. So again, we're going to use the work-energy theorem. The net work done will equal the kinetic energy at the end, point C, minus the kinetic energy at the start, point B. We're finding the work done from B to C, so it starts at B and it ends at C. So we're told that negative 0.75 joules of work is done. We already calculated the kinetic energy at point B was 1.1719 joules. And so we could calculate the kinetic energy at point C. If I add 1.1719 joules over, I get that the kinetic energy at point C is 0.4219 joules. Again, there was more negative work done, so that took away from the kinetic energy even more. It decreased from 1.17 down to 0.42. Now, this question asked us about the speed, so we can use the definition of kinetic energy. It's 1/2 times the mass of the object times the speed squared. So we know the mass, we know the kinetic energy, we can calculate the speed, and we get the speed is 0.75 meters per second. In the last part, it wants us to do almost exactly the same thing as in part B, but now it says how fast it would be moving if positive 0.75 joules of work were done from B to C. So that would mean that there would need to be an additional force that's pushing it forward, doing positive work on it. You know, there's friction taking it away, something else adding energy to it, and so together the total work done is positive 0.75 joules. So this means that the kinetic energy is going to increase. That means that the speed should increase from B to C now. So at the end, we should get an answer that's bigger than 1.25 meters per second. So again, we're going to use the net work done is the kinetic energy at C minus the kinetic energy at B. But now in this part, we're told we have positive 0.75 joules of work done. And that's going to be my kinetic energy at C minus 1.1719 joules, my kinetic energy at B. I again add 1.1719 joules to both sides. I get that the kinetic energy at point C now is 1.9219 joules. Again, the kinetic energy went up. It went from 1.1719 up to 1.9219 joules. And so then, to find the speed, kinetic energy is 1/2 the mass times the speed squared. So if I solve that for the speed, I get that the speed is 1.601 meters per second. Again, this is faster than it was moving at point B. It went from 1.25 meters per second, now it's moving 1.6 meters per second. So again, work is the way that we transfer energy to or from an object. So now this next problem, we're going to look at something similar to that. We have a car that's moving at 23 meters per second, and it slams on the brakes. The coefficient of friction between the rubber and the concrete is 0.7. So this car is going to skid to a stop. And we're going to use the work-energy theorem, or the work-energy principle, to calculate how far the car will slide before stopping. Now this is something that you could do with kinematics. A lot of these problems, if you could find the acceleration, if the acceleration is constant, you could use kinematics to solve it. We're going to show how to use the work-energy theorem to use this. And so with this car, we have three forces that are acting on the car. One of those forces is the force of gravity. So the force of gravity is 1,800 kilograms times 9.8 meters per second squared, which is 17,640 newtons. Another force is the normal force. In this, there are no other vertical forces acting. This car doesn't accelerate up or down at all, so the normal force has to balance out the force of gravity. So the size of the normal force is 17,640 newtons. Finally, we have the force of kinetic friction acting on this. The force of friction acts against its motion, so it's moving to the right. The force of friction is acting to the left. Again, there's no forward force pushing the car forward. The car is moving forward. It slams on the brakes. The wheels are locked. It's just sliding across the concrete, and so you have this force of friction, but that's it acting in the horizontal direction. And so we could calculate that force of friction. The force of kinetic friction is the coefficient of kinetic friction times the normal force. We're told that the coefficient of friction is 0.7. The normal force was 17,640 newtons. And that gives us a force of kinetic friction of 12,348 newtons. Okay, so we're trying to find what is this distance d that it slides before the speed is 0. And it says use the work-energy principle. Again, often you're not told what to do, so you could choose whichever method is most convenient. But we're going to use the work-energy principle. So this says the net work done will equal the change in kinetic energy. In this case, we have three forces acting. We have the force of gravity. The force of gravity does 0 work because there's no component of the force of gravity parallel to the motion of the object. We have the normal force. The normal force does 0 work because the normal force is perpendicular to the motion. There's no component of the normal force parallel to the motion of the object. And then we have friction. So this net work done is going to be the work done by friction. So we're going to need to calculate that work done by friction. So the work done by friction, first of all, the force of friction is opposite the direction it's moving. So if a force is in the same direction that the object is moving, that force does positive work. If the force is opposite the direction it's moving, that force does negative work. So this work done by friction is negative. And then we have the force of friction, which is 12,348 newtons. And then we have the distance d that it slides, which we don't know. We also have that the net work is the change in kinetic energy. And so this change in kinetic energy, it's 1/2 times 1,800 times the final speed of 0 squared minus 1/2 times 1,800 times 23 squared. So this change in kinetic energy is negative 476,100 joules. So the net work is the change in kinetic energy. The net work is the work done by friction. So that means that negative 12,348 newtons times D equals negative 476,100 joules. The negative signs divide out, and I get that the distance that it slides is 38.557 meters. So again, I knew what the force was, I knew how much energy needed to be taken away, and so I was able to figure out how far it slid, how big a distance that force was acting over. The second part of the question says, how far would the car travel if it was going twice as fast? Okay. So this is a conceptual idea. So kinetic energy is 1/2 mv squared. And so if it's going twice as fast, if I look at this, v squared is what kinetic energy depends on. So if I double the velocity, I have 2 squared, or 4 times as much kinetic energy. So the work done needs to be 4 times bigger. In this, we have the same force of friction acting. So if you have the same force, but we need 4 times as much work, that means it's going to be 4 times the distance. So doubling the speed does not double the distance that it takes to stop. Doubling the speed actually quadruples the distance that it takes to stop. When you're driving, that's one of the reasons that if you're on the expressway, you need to leave a much bigger distance between the cars, because you might say, oh, well, I'm only going twice as fast. I'm going 50 miles an hour instead of 25 miles an hour. But that actually means that it's going to take you 4 times the distance to stop that it would if you were traveling at 25 miles an hour. Okay, the last one that we'll look at in this video, we have a soccer ball that's initially moving at 3 meters per second. A soccer player kicks the ball, exerting a constant force of 50 newtons. That's probably not accurate to treat the force as being constant, but we're going to assume that he exerts a constant force of 50 newtons in the same direction as the ball's motion. And we're going to figure out what distance that force needs to act over so that the final speed is 6 meters per second. So I can find the kinetic energy that it starts with. It's 1/2 times the mass times the initial speed squared. So that initial kinetic energy is 1.89 joules. I also know what the speed is at the end. So my final kinetic energy is 1/2 times the mass of 0.42 kilograms times the final speed, 6 meters per second, that speed squared. And so my final kinetic energy is 7.56 joules. Okay, so this one is very similar to the car problem that we just did. We know the initial speed, we know the final speed, We know the force that's acting. We're looking for the distance. So if we know the initial and final kinetic energies, we know the net work done. The net work done will be the final kinetic energy minus the initial kinetic energy. So that's 7.56 joules minus 1.89 joules. And so that's 5.67 joules. And in this case, the net work done is the work done by the force of the player. So it's the force of 50 newtons times the distance d that it travels. So putting those two together, 50 newtons times d equals 5.67 joules. And so dividing by 50, we get that the distance is 0.1134 meters, which is about 11 centimeters. So this person's force is only exerting over a short distance to take the speed from 3 meters per second to 6 meters per second. So again, if you can calculate the work done by forces, you can use those to find the change in kinetic energy. But if you know the initial speeds and the final speeds, you can work your way backwards and look at the forces or the distances. So that's the power of this work-energy theorem. If you know the total work done, that will equal the change in kinetic energy. And it becomes even more powerful when we look at situations where the force is not constant. If we're able to find the total work done in those cases, we can still use this work-energy theorem. And so it allows us to do a lot more problems than kinematics would allow. We're going to record a few other videos that will have more sample problems involving work and kinetic energy, including some that will have non-constant forces. But this is a good start to some of the problems. So look over these things, and there will be more videos to come.